Right, I thought we'd just have a bit of a recap of some of the key concepts behind the system identification concept and what could go right and what could go wrong. So what we're going to be having is a real control system running with a controller, and you've got a real system here, and we're going to arrange to put a set point change at the input V, and that's going to run through the control system, and it's going to generate an input change in the control input U, which then generates a control in the output Y. And we need to make sure when we're doing this that there's sufficient excitation, so we don't want a little signal that does something like this and this just does something like that. We need something that excites the system, so we need like a good exciting signal here, good exciting signal here, so we can excite all the modes inside the system. The next thing that's going to happen is, because it's a real system, it's not going to start at 0. So we're going to have some value here, say USS, and another value here, YSS. And for system identification purposes, we'll have to remove these values from this data. So we'll subtract this value, so it now starts at 0. So it goes along and starts at 0 because we've subtracted this from the data. We've done the same thing here, we subtracted this from the data, and we'll get something like that there. So this time hopefully will be the same as that. Now what we can do now is we can use different methods for modelling the transfer function. So we could do trial and error, or we could use the MATLAB system identification toolbox. And one of the issues here now is you've got to choose the transfer function. So in the transfer function, GS, we've got zeros and we've got poles, and so you've got to choose how many poles and zeros you have. Now in simple systems, let's say first order, second or third order systems, you could, with no zeros, you could choose that. But if the system has some zeros in, or it's higher order, then it's quite tricky to intervene on a human level just to choose numbers. So then that's where the system identification package in MATLAB is handy, because in this one you can choose how many poles and zeros you want, and then that will have a good go at trying to find you a transfer function. The basic way it does that is it generates a model of the system. It takes the same input, this same input signal that you had in the real system, applies the same input signal to a model to give you a model output. So this will be, say, YR, this will be YM. Now, if it's a really good model, the shape here will be exactly the shape, same as this shape here. And at that point you could say, well, we've then got a good model for our system. Now, it might not work. So you could get responses looking like this. Now, if it's very sort of constant and like this is indicating that maybe the system is rate limiting. So that means that it's got a maximum amount it can go at, and so rather than sort of have a fast response, it might start to get a constant rate which is slower than the real system. This might indicate some degree of rate limiting, or you might just get a response that's far too slow, or you might get one that's like completely unstable or misbehaving. So if it's looking similar to the two, that's giving an idea that transfer function is good. If you're getting a model mismatch, it's indicating that the model that you've chosen isn't really suitable. Now there are lots of reasons for model mismatch. You could have the number of poles and zeros weren't correct. There might be some non-linear features in this system which aren't reflected in the model. And there are a number of non-linear features. The actuator here will have a saturation in. The system itself could have some non-linear properties. and the sensoring system might not be totally linear either. So there's quite a number of issues to take into account when you are looking at this. The controller in both cases is less liable to error because this is an algorithm with some software, so it tends to run the same every time. Typical things you might have here are what's called actuator saturations, whereby the actuator has a maximum value and a minimum value. It's like driving a car. Maximum value is when your foot is right down. Minimum value is with your foot off. You can't control it outside those regions. So it's represented by a saturation effect. The system itself, though, could also have non-linearities in. The actuators themselves might not be perfectly linear. So most of the problem's going to come from non-linear properties. Another issue which you've got with non-linear properties is that if you double the size of the input step, if the output perfectly doubles, then you know that you're in a linear region. But what can often happen in a control system is you do one step, you get something like this. You double the step, and it doesn't perform the same. You'd expect it to be just twice as big, but it might do something like that, indicating now that the system has gone non-linear here. And so this data from this type of step response isn't really suitable for system identification. If you halve the step size, and it did halve this, so it did something like that, and this looked as if this was half of this, then this would indicate that you were in the linear zone. So there's quite a job to get yourself a good model here, and it involves quite a number of aspects which you could describe. Once you've got a model though, so when you've got the output here looking quite similar to the output here, got a good fit between the two, you've got some reasonable confidence then that your model is good. So if your model's good, you could come now to take your model and design a little controller in Simulink. This could be done in Simulink. And then what you could do is you could use the MATLAB optimizer to optimize the controller. Now what that will do is that will give you a step response for the closed loop system whereby it's trying to really minimize this signal here. It's trying to minimize that area. So you should get a nice response from your simulation, not something that looks a bit like that or like that. Something that's quite good in terms of a transient response. So this could be MATLAB optimized. That'll give you a k hat of s. Now what you can do now is you can take this controller from your simulation and put it back into your real system. So this also now becomes k hat of s. So the controller here is the same as the controller here. And this is your predicted performance now. So if we now run this system for real, what we would hope to get, if the thing had worked well, then the transient response we get here would look exactly the same as what we've got here. So there'd be very little difference between the two. And then we could then claim that we've managed to obtain a model. We then tune the model, use the tuned gains on the system itself, and got a good correspondence between the closed loop simulation and the closed loop real system. Again, what can happen is in the real world, this might not work. So again, it's the same issues to do with modelling. There could be actuator saturations here. The system here might be a little bit non-linear in some of the actuators or some of the different aspects of it, and the sensing value can go wrong as well. And also you have to watch out for the size of the step. So you've got to make sure that you're operating the system within its linear zone. And those are the major issues, I think, to be covered in system identification and the use of modelling and simulation to design control systems. So hope you find that useful.